1, port 2, then you have S parameters. You don't learn S parameters. So I'll keep it simple and quick. So you see, the L is very much smaller than lambda, which means the frequency has to be very high. Okay? So this is KVL, KCL. I'm gonna skip this. This is a long element model. So it has R, L, G, C, and it has a mini resistance, inductance, conductance, capacitance, and this is how to calculate. I don't think this is gonna be, no. Maybe this will be tested. Did you mention this will be tested?
Don't know yet. 没记啊。
Page 22.
22, first stop.
Okay. Terminate the transmission line.
So,
Nice.
So this part is basically the derivation. So these two are basically the derivation of your later equations. So this one is the complex propagation constant. It has alpha, it has beta, right? Pay attention. This one is different from the one that you're going to use in the lossy medium. Your lossy medium is beta plus J alpha. So positive sign means incident wave. Negative sign means reflected wave. Always like this. If you say a plus, it means incident. If you say a minus, it is backward. Okay? So let's see. I'll just this is the amplitude. This is the amplitude, and this is minus gamma z. The gamma is the complex propagation constant. I don't know what else to say. So just a plus and minus sign over here. Pay attention to this. This is very important. Don't make a mistake on this. This is plus and this is minus. And the reason is because the current has directions. So the current has directions. So here just basically a very basic thing. Okay, we have 5 star over there. That is beta equals to omega to the square root of LC. So this case is a lossless transmission line. So basically I think almost all of your questions is going to have lossless transmission line. That is say that alpha, which is attenuation, is going to be 0. Then it just gives you beta. Beta is propagation constant as well. What is the name of beta? A phase constant. So alpha is attenuation and beta is phase constant. This is a lossless transmission line. So attenuation is 0, that is alpha is 0. So your gamma is going to just J beta. Then in this case, that is gamma equals to J beta. Okay. So this is Z naught. What is the meaning of Z naught? Z naught is the characteristic impedance. Okay. So in transmission lines, we often use K instead of beta. So you can just write beta and K, they're the same thing. So it changed to K here. Alright, and then this lambda equals to 2 pi over K. K is the wave number, and K is the phase constant, so K is the same thing. And we want to calculate calculate beta, that is this equation. Okay? So U is the phase velocity. Phase velocity is omega over K. So these are basically the formulas. And I go through very quickly, but they are very important and you might use. Right? And epsilon R is the relative permittivity of the dielectric material. So epsilon R. Then when we calculate material, we always use epsilon R dot epsilon naught. They usually come in together. So, right. You guys need to go back and read it yourself. after this. So this is a terminated transmission line, which is a very basic model when you deal with transmission line problems. So you can see here is the generator, and this is the impedance of the generator, and this is port 1, and this is port 2 with a load of impedance ZL, right? And then pay attention to the Z. The Z at this point is 0, and Z at this point is minus D. And the L here is 0, and the L here is D, positive D. So L is usually positive number, and Z has minus sign. Okay? This kind of positive and negative thing will sometimes cause you problems in your later calculations. Just pay attention to this. L is the length, which is a positive number, and Z is the negative one. Okay? So if ZL equals to Z naught, what does this mean? Translate into without a naught. Okay, this one, that is because he doesn't mention it. Yeah. Okay, for this one, that is because you have a two-port network right now. You have port 1 and port 2, right? So then why we engineers want to use this transmission line, because it is lossless. However, we this part is the transmission line. This is DL, and this is port 1. Okay, so this is transmission line with characteristic impedance of Z naught, and this one is ZL. Then the reflection coefficient gamma at this point, that is at how to say, L equals to 0, right? That is at the load. Gamma equals to ZL minus Z naught over ZL plus Z naught. If ZL equals to Z naught, then this one is 0, right? So this one is gamma. Gamma is reflection coefficient. You can see very clearly from the name of this gamma, that is to say, how much power is reflected back. Yeah, in this case, no power is reflected back. That is to say, all your power is safely transmitted from the transmission line to the load. This is the very ideal case, and that we want to achieve. Okay, so that is the reason why she writes it like this. If ZL equals to Z naught, all power are transmitted without any loss. Without any loss, that means no reflection, right? No reflection. Did I say wrong? No. Reflection coefficient is 0, means no reflection. Everything is transmitted. Let's see. So this is basically very basic thing, but this is a minus sign over here, right? This is minus. This is the plus. The minus here is because I mentioned the current. The current has direction, right? So this is a lifestyle thing. Two equations of volumes. About this, I just want to say, I really have nothing to say about this one. This is just formulas. About this, this is just formulas. Okay. And this one is not very useful. I think there's another one that is much more useful later. We're going to read this one. Anyway, this one is very important. Okay, this one. That is the telegrapher equation. So ZL equals to V over I. That is to say, it asks you to calculate the impedance at any point on this transmission line. Any point. Like at this point, your L, this point you have L, right? Then what is the impedance at this point? What is the impedance? Then you can use this calculation. Alright? And the control factor is the KL. K is the beta thing. K is just beta. Yes. Right? So this is very important because right now you know the Z0, that is the characteristic impedance. You know the ZL, that is the load impedance, and you also know the KL. So sometimes this is KL, right? K equals to 2 pi over lambda. L sometimes we might give you like a quarter wavelength, right? Then the lambda can just get cancelled. So this one is just pi over 2. So just an example. Now, this is define a reflection coefficient, right? This is the calculation, right? At the load L equals to 0 as gamma L. So, yeah, this is how we get this equation, but roughly we use this one directly. Okay? So gamma equals to reflected over incident. Reflected over incident because it is called the reflection coefficient. How much it is reflected compared to the incident energy, right? So the reflected is the minus. Minus 1 is reflected, positive is incident. So these are the magnitude. And this one is jk minus jkz. This one is the z. Z here is 0. And because this is a reflected, so this one is minus, this one is incident, this one is positive. You can refer back to the previous slides. So this one is V over V, and this one is V naught minus, that is reflected V naught. Right? Reflected V naught equals to half IL ZL minus V naught. So we have sorry? This is page 24. So we substitute this one, then we can get the final gamma L. This one is to calculate gamma L. Please don't use this one to calculate the gamma at any point here. Okay? This one is to calculate the gamma L. If you want to calculate gamma at any point, then you have another equation with addition of e to the power of minus j to KL. Okay? So at this point, the gamma is calculated by this. But at this point, the gamma should be calculated at this one. Okay? This one. So, yeah. But as long as you know the impedance as the L, then you can also use this one. But usually we don't know. At the position of the generator, so the generator is basically the point 1. Point 1, that is L equals to D. That is the length of the transmission line, right? So this one is the telegrapher equations with the substitution of L to D. Okay? So this is gamma, which is the same. Yeah, D is the total length of transmission line. Right? So So this is a summary. Then we have questions. We have examples. So the examples I think is very straightforward. Is it? It has a 100 ohm transmission line. Connect to a load consists of a 50 ohm resistor incidence of a. So this one is a characteristic impedance, that is Z0, right? And this one, and this one, you need to calculate. You need to use to calculate the ZL because they are the load, right? Load consists of, what is this load? The load consists of a resistor and a capacitor. Okay, so first one is to find the reflection coefficient gamma L at the load for a certain frequency signal. So gamma L, we have that equation, right? Yeah, gamma L, we have that equation. It just or divided by Z naught, then he has this one. Right, so this one you just substitute and then you can calculate. Problem about this? Any problem about this? Any problem about this?
这个怎么算呢？可以
这个计算器可以直接算，
计算器啊。
可以直接算，
好，
所以可能
Yeah, just get familiar with the calculators. Don't figure out when you are doing the exams. Okay. So here is Z log load. Load equals to R minus J over omega C. No problem about this. So then you can get a reflection coefficient. So the second one is to find the impedance Z in at the input end of the transmission line if the length is. So what is Z in? Z in is this. That is Z in at the input port. Right? So the Z in is actually the L equals to D. Right? So then we have a telegraph equations that is Z equals to Z equals to Z naught ZL and beta L and beta L Z. So this is our telegraph equations, right? Then this one we just need to substitute L equals to D.
So for here, L and D, they are opposite direction. Then should I
No,
find the
they're
CF?
not opposite direction. They don't have direction.
They don't have direction.
L and D, they are just a number. They're just the length.
Oh, okay.
Yeah. But Z has direction. I mean Z has a negative sign.
Yes, GS negative sign.
So this part, if you want to calculate the input port impedance, we just need to substitute the telegraph equations with to replace L with D. Okay, and then the rest, the ZL we calculated for the first equation, right? CL is here, so we can calculate Z in. Any question about this part? I think it's very straightforward, right? So, second question is, a lossless transmission line with characteristic of 50 ohm and D equal to 5.3 lambda connects to a VG to a terminal load of ZL. It is known as VG and VG. So find the current I and voltage at the left terminal of the transmission line. So right now you don't have just one simple port. At this point you have VG and ZG. Right? So when you calculate about the voltage, then you need to use the voltage division. To calculate I here. Then how to calculate I here? We need to know the voltage and we need to know the impedance. Yes. So we need to know the voltage over here and the impedance over here. That is Zi, right? So now let's see how to calculate the Zi. Zi is basically the ZL, that is the telegraph equations with replace L to D. Right? When you replace the L with the D, then you can calculate Zi. Again, this telegraph equation is to help you to calculate impedance at any point with respect to the load. As long as you know the load impedance and as long as you know the distance between the load and the observing point, that is L, then you can calculate the C, that is impedance at your observation point. So then I can calculate Zi, right? At this point I can calculate Zi. Then what is Vi? Now we get Zi. Vi is actually the voltage over here, right? So the total voltage is Vg. then how much voltage you have is actually how much ratio of your impedance over the total impedance. So you can calculate you can calculate VI equals to VG, and this is CI plus ZG, voltage division. Okay, so that is how you calculate VI. Right now, then I think that's enough for the first question. So the second question is, what is IL and what is VL? So what is IL, what is VL? We know the Z load, right? And we also know the VI. And then we know the VI, then we can calculate the VL. There is a equation, remember?